UK, thank you, in which, let's press got it, just. So in which the students are doing their 4th year of their degree, their master's part of their degree, their research part here with scientists here. And they start in about end of August, beginning of September, and they have to hand their theses in middle of May, and they did that last weekend. So then they get a few days to write their talks. Their presentations will be 10 minutes each, and there will be 2 minutes for questions. So fairly quickly going through these. So it's more almost like a AAS talk almost. That's pretty much it. I will hand over to our first speaker, who is Joe Hall. And Joe hails from Stroud in the UK, which is in Gloucestershire, for those of you who don't know, which I'm sure everyone knew that. So Joe is still sort of looking for PhD programs, but he wants to go into the modeling of exoplanet atmospheres, which sort of is what his project was based on. So Joe, in his pastimes, he likes biking, and he actually did competitive archery for the University of Southampton. So he's well armed if questions get difficult. Okay, so he's going to be talking about modeling X-ray transits of the hot Jupiter HD 189733AB.
Yeah, I think I said to Jeremy I'm into baking, not biking, but
baking.
they're near enough the same thing. So yeah, I've been looking at modeling the X-ray transits of this hot Jupiter over the last 8 months using simulations. But that was the wrong slide. I went straight to the end. Sorry. So just to provide some background, the transit detections are play a major role in the discoveries and observations we can make of planets around other stars. Investigating exoplanets has been identified as well by the Astro 2020 Decadal study as a key pathway to discovery. So looking at habitability and what makes up an exoplanet is all very big things. But for this project, I've been looking at hot Jupiters, which are large planets close into their star, so hence the name. And at the bottom here, we just have a quick image showing how a transit can be observed. So when a planet moves in front of the star, we see a reduction in light during the transit. So specifically, we've been looking at HD 189733AB. It is so far the only published example of an Exo-Jupiter with a transit accessible in the X-ray domain. It orbits the star HD 189733A, which is in a binary system. However, since its sibling planet is without its sibling star doesn't have a planet, it means it makes it suitable for modeling detection, and we can separate them out as there are no star-planet interactions present around HD 189733B. The X-ray emission we observe comes from the stellar corona around the star, which is an optically thin shell, or optically thin to the X-ray shell around the solid core of the star. As such, we observe what is known as limb brightening, which you can see roughly here on this extreme ultraviolet image of our sun as the emission peaks at the edges of the star. As such, during the transit, we expect to see a W-shaped light curve as light gets absorbed at the edges. So Poppenhager et al. Found that for HD 189733AB, there was a transit around 3 times deeper than the optical. So this is the extracted light curve from Chandra observations, and then behind that you can see in blue the optical light curve. And you can see just from that the transit in X-ray is deeper. So as such, Poppenhager estimated that there was an extended X-ray atmosphere about 70% larger than the optical radius. So we've been looking at modeling this atmosphere, trying to constrain the size and its density and its chemical makeup. So to do this, we took 6 observation IDs of the system using Chandra. We converted the event times in these event files from time to phase to produce event lists in the source region. From this, we ran DM extract on each of the individual files to produce light curves. And in the top there, I'm showing OBS ID 12341, which featured a phase during transit. So we should feature the flare during the transit. And as such, we decided to disregard that for later steps. We then combined the files to produce the combined light curve, and then extracted the spectrum, which we fitted using a 2-component XSV APIC spectral fit in Sherpa, which gave us component-wise flux and count spectra. These were then sent to our simulation. So the simulation itself, the first thing we did was define a set of the key parameters we wanted to investigate, sorry. So we had scale height, so how large the atmosphere was, the abundance of carbon, nitrogen, oxygen making up the atmosphere, as well as a base density value. So using the scale height and the base density, we did path projection through the atmosphere to produce 2-dimensional column density maps. So these column densities, each pixel there has a different column density assigned to it. So these column density maps were then combined with our spectral fit results from Sherpa, as well as our abundances, to produce a new model which had an XSV fabs absorption component multiplied to it. So iterating over each of those column densities, we were able to produce an image of the planet's atmosphere, where at each spectral point, I've flattened it into 2D here to show it, but in the actual simulation itself, this is a 3D image where each point in that image has a full spectrum assigned to it of different intensities, which meant that we can customize which pass band we look at when producing our model light curves. So we then used orbital parameters to move these images in front of AIA images of our sun, which had a coronal component added to them. So I've shown here just what that coronal component looks like. Averaging over these 60 light curves allows us to then produce an average model light curve, which we could then fit to the data. And by evaluating that fit, it informed which grid point we should move to next and what other areas of grid space we would need to look into in order to isolate the best fitting parameter. So this is a little movie of the simulated transit. So from left to right, we have what the light curve looks like at each time step. And you can see already from this, it's exhibiting that W shape. In the middle, we have the small image of the planet moving across the face of the star. And at the top right, we have the spectrum at each time step, and underneath that, the ratio of that spectrum to the emitted spectrum. And you can see how it changes over time, but in particular at the lower energy wavelengths. So the parameter space we explored covered in total around 1,000 values to produce our results. We used a range of scale heights and densities, and we focused on 3 CNO abundances so far, but we are currently simulating for more of those as well. So this was our best fitting result. We found this at 0.35 plus minus 0.05 R-Jupiter for scale height, base density of 1.1 plus minus 0.8 times 10 to the 15 atoms per centimeter cubed, and a carbon, nitrogen, oxygen abundance of 5. And from this, you can see how the average transit depth, the mean transit depth, was about 9%. So what Copenhagen et al. Had found was 7.5%. We found 9%. We've also found that our best fitting atmosphere is smaller than theirs, only about 30% larger than the atmosphere of the planet. So where they found 70% is just due to we also estimated a higher base density. So they estimated base density on the order of 10 to the 12, 10 to the 13 atoms per centimeter cubed. And so the reason why it's possible that both of these values could be true is shown in this distribution of chi-squared. So from left to right here, we have abundance increasing. So we've got carbon, so CNO abundance of 1 relative to solar, 5, and then 10. And on the x-axis, we plotted scale height, and on the y-axis, we plotted density. The colored contour regions relate to delta chi-squared compared to the minimum chi-squared value of each density, whereas the crosshatch region is the delta chi-squared plus 1 for the CNO when compared to the best fit from CNO equals 5 here. So from this, you can see that at high densities, you find that low scale heights fit well to the observations. it's also true that at high scale heights, low densities fit well. So this has made constraining our uncertainties quite difficult, and as it both are potentially valid solutions. So just to summarize briefly, we have successfully been able to simulate the X-ray transits of HD 189733. We found its best fitting region at 0.35 R-Jupiter with a base density of 1.1 times 10 to the 15 atoms per centimeter cubed, a CNO abundance of 5. However, there is still work we need to do to continue and better constrain these results. For example, we want to look at more scale heights to get a better handle on the uncertainties. We want to look at more densities. We also want to look at more abundances. And the other thing, another big change we want to do is start calculating Poisson likelihoods rather than chi-squared. So using the Poisson likelihoods would allow us to look at individual spot distributions on the stars and allow us to fit the systematic errors from those results. And I'd just like to ask now if there are any questions.
Questions? Yes.
Yeah, I have some of the off-topic question, but so Rosanna and Stefano and her team, they found this like perhaps planet around like an X-ray binary, and I guess that it's a very different system. But is there anything we can learn from the transited X-ray here, say the statistics, since you know here that it's like a confirmed exoplanet that would be applicable to understanding how much to trust that source?
Possibly, but the advantage it is different as that's around an X-ray binary, whereas this is just around a normal, well, a normalish star. So it's different physics there governing the emission, but it's possible, yeah, I would assume. Okay.
Josh,
what is the spectral type of the star and the other star in the system since it's binary, right?
I don't know that. I'm afraid I would need to.
That flare you showed suggests that it's, you know, must be pretty active.
It's an active star, yeah.
Is it M-Dwarf, or do you know?
I don't know.
Certainly not.
someone must
Scott knows.
Yeah, it's a K7. It's a K7.
K7.
Yeah, okay.
Okay, yes.
Great. Well, so I have a couple questions. One, when you talk about the CNO abundance, what units are you talking about?
So that's relative to Gravas and Saval's measure of abundances of elements in our sun.
Okay. Thank you. And then, so this is a lot of degeneracy between the two. What can you hear about other predictions that you could make from your model?
Not really, I'm afraid, from that. It's just that both parameters affect the depth of the transit we observe, since a larger scale height has a larger atmosphere absorbing, and larger density affects the amount of light absorbed. So it changes the shape of the light curve somewhat. So for a larger scale height, what we see is we don't see the W shape, we just see a flat transit, for example.
Right, but I mean, for example, right, like would you also be able to make predictions like optical just in that case, or are all your models?
I don't know, I'm afraid, sorry.
Yeah, the X-ray absorption is above the optical focus.
Yeah.
So it's for all intents and purposes here, the optical is okay.
Could you repeat the questions? We cannot hear at all over here.
Federico, do you know if there's any tweak on the owl that cuts the questions? I'm sorry, I saw you had your hand up.
If
you on, sorry,
typically, if you try to speak a bit louder, they could hear from. So the question was about the degeneracy between the two parameters. I guess you figured from the answers.
Yeah, Vinay, sorry, we're going to have to move on. Let's thank Joe again for. Okay, so next up we have Tom, and Tom hails from Guernsey, which you may or may not know is one of the Channel Islands in France. It's actually where my parents went for their honeymoon. Very popular honeymoon destination in the 50s. So Tom, no, we actually have my glasses here so I can read this properly. So Tom is into hiking. I think he said biking there. He's into hiking. And let's see, he's going to do a PhD at Jodrell Bank, the University of Manchester, working with Chris Consolis. And Tom's talk is on signatures of feedback in the spectacular extended mission line region of NGC 5972.
Thank you very much, Jeremy. Yeah, so I'm going to be talking about NGC 5972 and the work I've been doing with Peter Maxim and some of my other wonderful co-collaborators. But firstly, I actually want to talk about a completely different object. So you may have heard of it or you may not, but Hani's 4-Vert is a very, very interesting object that was discovered back in 2007 by Hani von Arco as part of the Galaxy Zoo program. And what makes it so interesting is that it's the first known example of a quasar light echo, which means that using this object, Hani's 4-Vert is this green region of highly ionized O3-emitting gas. We can make inferences about the luminosity of its parent quasar, IC 2497, shown above, over much longer, timescales much, much longer than humans. I want to briefly explain how that is done. So I've drawn a very simple diagram here, so you can see in the center, I'll just turn the laser pointer on. You can see your stereotypical black hole surrounded by an accretion disk of an obscuring torus, and above and below the accretion disk, we might expect a bicone region where the obscuration is less, where the AGN emission is less obscured. And if there is a significant region of extraplanar gas, which can be ionized by the AGN emission, we can see what's known as an extended emission line region, which is gas ionized by an AGN spectrum, but on much larger distances, so greater than 10 kiloparsecs than we would normally see. And we can measure the luminosity of this cloud, and we can measure the luminosity of the actual nucleus itself. But we don't think that on long time scales, the luminosity of these AGN are not constant, and are related to the accretion happening within the accretion disk. And that, we think that happens on 10 to the 5-year time scales of rapid accretion followed by longer quiescent phases. So if jumping forward in time, the accretion rate decreases and the bolometric luminosity of the AGN decreases as well. But given the light travel time and the recombination time scale of the ionized gas, the luminosity of the cloud is much, much higher than the bolometric luminosity of the AGN. So by comparing these two quantities and estimating projected distance for the cloud, we can make estimates of what the luminosity must have been in the past, assuming that at some point the black hole emission did balance what we see from the EELR. So that lets us look up on timescales as long as 100,000 years. And why is this important? So we think in X-ray binaries, we can make a comparison to those, that the emission occurs sort of in two states. You have a hard and a soft state, which correspond to specific spectral and timing properties. And the hard state specifically corresponds to a low Eddington rate accretion. And in that accretion, we think we see a lot of the luminosity of the AGN appearing in the kinetic form, which can influence the interstellar medium. So when we take that to AGN with known long-term decreases in variability. So for example, Hani's 4-Vert that I said, the host, we've used Hani's 4-Vert to show that IC2497 has decreased in luminosity about 50 times in the last 100,000 years. So with known variability, we think that in a way analogous to X-ray binaries, that the supermassive black holes within AGN may be in a kinetic or feedback mode where they're doing real work on the interstellar medium of their host and affecting the star formation rate or inflating or blowing bubbles. And a rough guide to estimate this is comparing the kinetic and the bolometric luminosity. And Hopkins and Elvis wrote a paper in 2010, which estimated that for a 2-stage feedback model where the hot, warm ISM is entrained by a small scale outflow and then carried on, the cold star forming ISM is then later expelled as well. You need about 0.5% of the bolometric luminosity in a kinetic form. So I've been looking at Chandra and Hubble observations of NGC 5972, which is this one. It has the most extended known emission line region, and they called them 4-Verpius because Hani's 4-Vert is Dutch for basically Hani's thing, and Voorwerpjes is just Dutch for small thing, essentially. So a little bit about NGC 5972. It has the most extended known emission line region. You can see from tip to tail, it extends about 70 kiloparsecs, and it has this double helix shaped emission line region. And in the center, there is an arc-second scale nuclear bubble containing the central engine. And that central engine is the bubble we think might be a signature or feedback related to the current mode. So I've been looking at the Chandra and the Hubble observations. And here's some of my results. So as you can see, it's a complex galaxy. It's radio loud with a classic double-lobed radio structure, seen here. And then in this image, you can see a close-up of the galaxy, and the blue overlaid shows the soft X-ray emission, which you can see is coincident with the EELR. And that's interesting because with a potential longer observation, we might be able to use the soft X-ray emission as a variability probe on much longer timescales than the optical emission. So you can use the X-ray emission to probe maybe 10 to the 6 or 10 to the 7 years variability. So I'm going to zoom in on the bubble, which is this region in the center here, and just going to talk about that briefly about that. So we see a X-ray, soft X-ray, and hard X-ray emission coincident with the bubble, from 0.5 to 2 keV, and we see that this emission is extended, spatially extended. So I ran simulations of the Chandra point spread function and found that specifically in the soft band that this emission is above the PSF, and interestingly, it's most above the PSF. It's most extended in the east quadrant, which is the same direction as the O3 emitting gas, which is what's shown with these blue contours. So we see a coincident X-ray and soft and O3 emitting population. I've also looked at the kinematics. So you can see here, this is the Estes spectral extraction slit for the AGN across the long axis of this bubble feature. So we can measure the velocity of the gas from fitting emission lines. And the kinematics are complex. We measure the continually distinct dispersion velocity for the O3 gas, which is much higher than we see in the H alpha or the N2 profiles. And we see across the bubble, we see a sort of a kinematic profile that doesn't really match with the models that we have. So Fisher et al. Did some modeling of what a potential this sort of velocity map could look like for AGN with a similar implied inclination, and it doesn't quite match up. And it may be that we haven't constrained the actual inclination of this AGN that well, but there's further work needs to be done on that. I've also looked at the spectroscopy. So I fitted an AGN torus model to the emission from the bubble, which contains the nuclear source emission. So a physically motivated model for the hard emission, and then introducing models for the softer emission that model of a hot extended gas within the outflow. So we see a double APEC model, and an APEC model models gas that's been photoionized, by collisionally, a thermal plasma, and a cloudy model is plasma that's been ionized by an AGN spectrum. And our spectra are consistent with both, but from the APEC model, we can calculate some parameters, and I just want to draw your attention to a couple of them. So a shock velocity lets us work out, estimate velocities of the types of outflows we would expect to see in this bubble. And being above the sound speed suggests that we could potentially see shocked emission where the outflow is shocking the precursor ISM. And the crossing time gives us an estimate of the overall, the age of a lower limit on the age of the bubble, of which 2.1 million years is much longer than the current variability, which is around 50,000 years for this galaxy. So it's decreased in luminosity about 100 times for the last 50,000 years. So I also want to talk about that. So I mentioned the ratio of the kinetic and the volumetric luminosity earlier. I find a lower limit of 0.8%, which suggests that we could be seeing efficient feedback within this galaxy, which may cause the gas to disperse on long timescales. but a word of caution there is that given we know that the volumetric luminosity has decreased on recent timescales, it's 1% of what it was 50,000 years ago. But the kinetic luminosity is estimated from this hot X-ray component, which doesn't respond quickly to changes in the X-ray, in the volumetric luminosity. So this estimate may be an overestimate of the true efficiency, and it may be lower than this value. And yeah, to briefly talk about the outflows, the maximum velocity we saw here was around 300 kilometers per second for the O3 component. And given a reasonable line of sight projection effect, this could be a part of the outflow. So here are my summaries. So basically, galaxies containing extended emission line regions allow us to probe variability of AGN on much longer timescales than we could ever hope to probe, without having observations for thousands and thousands of years. The current feedback processes are much older than current variability, so they may be related to a previous decrease in output. We think that these are cyclical, so it could be previous. And yeah, the future X-ray observations are a really interesting way we might be able to probe longer timescales and average over the individual duty cycles of AGN. I'm happy to take any questions.
Thank you very much, Tom. Time for just 2 questions. Yes, you were at first, I think.
Tom, a great talk. Is the quasar in the middle of the double helix, or is the helix in front of the quasar?
Yeah, good question. So the double helix is above and below the quasar within the bicone region. So the AGN is right center. We think there's a slight inclination. So one of these arms aren't exactly face on in the plane of the sky there. It's tilted, but in that plane it's directly in line between the two. It's obscured by this, so it's constant fit. So it's a high column density of gas within the bubble, and above and below we see the arms. So the arms aren't directly in front.
The variability of the direction of the outflow is function of time.
Yes, so you can make estimates as to and there are potential interesting like substructures and stuff that you can look into to look for like longer term outflow variations. But I didn't really have time to go into too much of that.
Okay, one more quick question. Okay, let's thank Tom very much again.
Thank you very much.
I've been remiss in not saying who was supervising the students, so apologies for that. Tom was supervised by Peter Maxim, and Joe earlier on was supervised by Vinay Kashyap. Right, so next up we have Zach Irving. Zach is from Huddersfield in West Yorkshire, and his favourite pastime, again well able to defend himself against questions, is jiu-jitsu. He's going on to do a PhD with the Southampton equivalent of my side, who runs the Southampton side of the exchange program, Diego Altamirano. So Zach is supervised by Brad Wargeline, and he's going to be talking about magnetic cycles in fully convective M-Dwarfs from photometric time series.
Thank you, Jeremy. So some background here, stars. This is quite a reductionist view, but stars are essentially big bar magnets, much like the Earth. And these bar magnets undergo quasi-periodic polarity reversals. In the Earth, this happens every few 100,000 years, but in stars, because movement of material is much more, it happens much more aggressively, they're more magnetically active, and you get polarity reversals much more quickly. So in the sun, this happens about every 11 years. And obviously we can't see these magnetic field lines, but there are ways we can infer magnetic properties. And one of the easiest is to use star spots. So during the solar cycle, these star spots migrate towards the equator. And then when the polarity flips, these star spots transition to the opposite hemisphere. So more background here, the solar cycle is best described by an alpha omega dynamo. So this has two components. It has an alpha component and an omega component. The alpha effect is caused by cyclonic convection. So obviously, if I get my laser pointer here. So cyclonic convection happens in the convective zone. I can't see that pointer. But that's caused by Coriolis forces and magnetic forces. And then the omega effect is caused by shearing due to differential rotation. And in the sun, we believe that this omega effect happens in the tachocline, which is in the convective zone, radiation zone boundary here, which again, you can't really see very well. But in stars later than type M3.5, which we expect to be fully convective, you don't have a tachocline because there is no boundary between the convective zone and the radiation zone. So these stars cannot support solar-like alpha omega dynamos. However, Suarez-Mascherano 2016 found evidence for cycles in stars ranging from G0 to M6. So that covers the fully convective stars using ASAS3 data. ASAS3 is shown on the right here. It's an automated all-sky survey, just doing a simple aperture photometry. One of the stars that Suarez-Mascherano looked at is Proxima Centauri, which is our nearest neighboring star, which is type M5.5. So that's well into the fully convective regime. And Wagel in 2017 confirmed this 7-year period, which was proposed by Suarez-Mascherano using coronal X-ray observations, because this is the only star with long-term X-ray monitoring, apart from our sun. So this goes to show that photometric data are somewhat correlated with magnetic activity, but they're not the best tracer. And that's because we have complicated other effects which can obscure magnetic activity in photometric data. But the good thing about photometric data is we have an abundance of unbiased observations, thanks to all-sky surveys like ASAS3. So what have I done? I've reanalyzed some of the M-Dwarfs from Suarez-Mascherano 2016 using the same ASAS3 data that they used and newer Assassin data. Assassin is another automated all-sky survey mission, and it basically improves on ASAS3 in every meaningful way. It has higher observing cadence, better signal to noise, it's just etc. It's better in every way. And I've compared traditional techniques such as Lomskargo periodograms, which is the time series analysis tool of choice that uses sign fitting to identify periodicities. And I've compared that with innovative new techniques known as Gaussian processes. Gaussian processes are a machine learning technique which you can use to model data sets. And the benefit of this is you can have more flexible models rather than just a strict sign function. So you can model the quasi-periodicities much better. And here I've compared my sign fits with my Gaussian process fits. So at the top is just a simple superposition of sign functions. On the bottom is the Gaussian process fit. And this is just for one of my stars, and you can see the models are fairly similar. So the main takeaway here is just that these cyclic modulations, while they don't have to be sinusoidal or strictly periodic, they can be well approximated by signs. So here are, if I can move this. So here are my results. My results are on the left column here, and the Suarez-Mascherano results are on the right. And you can see that I confirm most of these cycles with periods which are within error of their results. But they find some periods which I don't because they tolerate a lower false alarm probability threshold, or I suppose a higher false alarm probability threshold, whereas I was only selecting cycles with false alarm probabilities less than or equal to 0.1%. And the Assassin data, which are shown in the middle here, the periods, they show somewhat different periods, which could just be a result of the improved data set. And Assassin results also show sometimes a single star can exhibit multiple cycles. And this is seen in FGK stars, for example, Brandenburg 1999. One of my most surprising results was that the cycle period and amplitude of these M-Dwarfs appears to be correlated. This is not something that Suarez-Mascherano looked at, so we can't really compare we can't look at how these M-Dwarfs compare with FGK stars, but that'll be something interesting to look at for sure. Now, using FGK data from Brandenburg 99 and Leighton in 2016, I was able to compare the ratio of cycle period to rotation period against inverse Rossby number. So the Rossby number, for those of you that don't know, is the rotation period divided by the convective turnover time. And the convective turnover time is how long it takes material to move from the bottom of the convective envelope to the top, or vice versa. So this is a good metric to use to compare stars with different sized convective zones, because it kind of normalizes for differences in convective zone depth and also temperature. And using, I should also mention that I use theoretical convective turnover times from Barnes and Kim 2010. So these two groups of stars here, these are the FGKs from Brandenburg and Leighton, and these are my M-Dwarfs. You can see they're both described by separate power laws, but the slope of these power laws is the same, which suggests, assuming a linear omega effect scaling, this suggests that the alpha effect is quenched in both FGK and M-type stars, So as the rotation period gets longer, the alpha effect gets suppressed. And that's consistent with theoretical models, for example, Kitchetinov and Rudinger, 1999. Now, if you look at this gap between these two groups of stars here, it's unclear if this is a real effect or if this is just due to my limited sample of stars. But one explanation for this could be because my M-Dwarfs have larger convective zones, they obviously need a larger rotation period to get equivalent Rossby numbers. And this would mean that the Coriolis forces in the convective zones are weaker, and that would give you a weaker alpha effect. And if that is why these two groups of stars are disjointed, you would expect a smooth transition from here to here. But this gap could just be, again, an effect of my limited sample. Or it could be something real. And if it's something real, one explanation could be that because M-Dwarfs are cooler than FGK stars, they have a lower average convective velocity. And it may be the case that the convective velocity has fallen below some critical value relative to the mean magnetic field strength, which would cause a sudden drop in the alpha effect, and then that's why you get this gap. But to really understand what this gap is, and if it's real, we kind of need to just observe more stars covering more of this space. So in summary, I've found or confirmed evidence for magnetic cycles in 12 M-type stars, 9 of which were of type M3.5 or later. And the periods and amplitudes of these cycles appear to be related by power law, which is the fact that these stars have cycles at all is surprising, and the fact that these periods and amplitudes are correlated is also surprising. I've also found that the alpha effect appears to be reduced in M-Dwarfs relative to FGK, which could be due to the convective velocity falling below some critical value, or it could be because the convective zones are larger. You need a longer rotation period to get the same Rossby number, and you would expect a smooth transition from FGK to M. And I've also found that the alpha effect is quenched in FGK and M-type stars alike, and you don't really see a difference in the quenching as stars transition to fully convective, which is, again, another interesting result because these stars don't have, most of these stars don't have taper points. So the fact that they have the same quenching is unexpected. So I'm happy to now take any questions.
Thank you very much, Zach. Any questions for Zach? We also haven't been looking at online questions. You can maybe wave at me if you see an online question. Zach, one thing that puzzles me then is if the fully convective M-Dwarfs have similar dynamo behavior to the sun, what does that mean?
It means that, if I go back to my diagram here, so this one, it could mean that the tachocline is not as crucial to these dynamos as we expect. It may be that the shearing can happen in the convective zone, and you can store magnetic energy in there. But it just means that even though they shouldn't have, or at least we don't think they should have the same cyclic behavior as the sun, they do. So it means that our understanding of the cycle in the sun is maybe wrong.
Okay. Any other questions? Okay, well, let's thank Zach again. Oh, there is a hand up. No, that's a clapping hand. Sorry. Yeah. Okay. So next up, we have Ben RIcketts. Ben's project was supervised jointly by Jack Steiner and Cecilia Garappo. Ben hails from, puts glasses on, East Sussex near Brighton, and his pastimes really are biking and hiking. He is going to do a PhD at the University of Amsterdam at ESRON. And ESRON, of course, is a big collaborator of ours on the Chandra program, since they're the PI team of the low energy transmission grating spectrometer. And he's going to be working with Daniela
Huppenkeithen.
And his project is going to be talking about the mapping the X-ray variability patterns of GRS 1915 + 105 with machine learning.
Thanks, Jeremy. Okay, so what is GRS 1915? So GRS 1915 is a low mass X-ray binary system within our Milky Way. It's on the heavier end of low mass X-ray binary systems with 12-point solar masses. It's extremely optically obscured due to galactic dust. So we pretty much view it exclusively within the X-ray. GS-1915 itself is very odd. It has extremely variable flux in the X-ray. It's very bright, on the order of thousands of counts a second. And it exhibits an incredibly large variety of variability patterns within that X-ray. It's also been in continuous outbursts for about 30 years. For context, kind of an X-ray binary system like these are usually an outburst for maybe a year or so. So talking about those X-ray variability kind of modes. So here is an example. So back in 2000, Bologna et al. Basically went through lots of archive data of GS-1915 and grouped kind of behavior into broadly kind of 12 classes. This is one of the classes called gamma. So on the top panel, we have a color diagram of X-ray color, showing this kind of weird distribution here. And then on the bottom, we have a time domain light curve showing rates on the y-axis and time on the x-axis. So here is all 12 of Bologna, and you can immediately see there is a huge variety of different kind of length scales of behavior, flaring, kind of long transitions between high and low intensities. It's a very odd source. And these cycles, they're not off kind of just random out of the blue. They repeat for sometimes like months or even like a year or so on month-long timescales. So they aren't just weird exceptions. They come up over and over and over again. So how does machine learning come into this? So Bologna he made this kind of system of breaking up these patterns kind of more as a descriptive way of kind of trying to break down and understand GS-1915's behavior. But we wanted to try and take that to the extreme and get a machine learning network to try and find if these are kind of intrinsic classes. Are these truly repeated behavior, which were they just picked up by Bologna by eye and you sort of, are these truly unique? So we used a method called autoencoders. The main principle here is an autoencoder will take an input of, for our case, time domain light curves and X-ray colors, and compress it down into a bottleneck of information. So for this, for ours, we use 256-second long time domain light curves and X-ray color in the time domain. We compress it down to 16 numbers. And the important part here is we use that code and we try and reconstruct the original input data that we put in. And if it's accurate, we're hoping to have retrieved important features, complex features from the original input. So I have an example here of inputs, for instance. So in the blue is the original data and the red is the reconstructed. So we use observation, we use all of our, the Rossi X-ray timing explorers, proportional counter arrays archive of GS-1915, which amounted to about 2100 kiloseconds of data. We break this into 256 seconds segments. And you can see here is a histogram of the amount of segments of a given, shown with a given class. So these classes, they are very disproportionate in how much they come up. So chi is very common, and then there's a lot of less common examples as well. So coming into here, you'll immediately see that these reconstructions are not perhaps ideal. They do not have the same, they don't have very fine resolution, which is a result of some of the architecture we used. But the main thing here is that it managed to pick up some of these complex features and was able to generalize this across a huge variety of different shapes of light curves. So we have intensity on the top and then 2 X-ray colors. So once we had all of our codes from our machine learning network, we needed an easy way to visualize kind of how the network was grouping up these kind of complex light curves. So we used something called UMAP, which is Uniform Manifold Approximation Projection, to visualize the distribution of these codes. So UMAP is a bit similar to principal component analysis and TS&E, if you've ever heard of those, where it takes higher dimensional data and projects it onto these lower dimensions here. So this is a pretty artificial construct for our ability to understand how the network is relating stuff to each other. So the first thing you'll see is there's three main kind of groups. We have a central one here at the top, which we call the brain, and on the right here, we call this the flag, and then here on the bottom, we have nicknamed this the horn. So straight away, all the different colors show the individual classes under Bologna's system, and you'll see it looks pretty messy. It's quite hard to understand what's going on. There's a lot of classes, there's a lot of points. So breaking it into different classes, we suddenly see that each of these classes kind of are distributed around these three clusters differently. So for instance, alpha is distributed across all three of these main clusters that I named. But for instance, phi is constrained only to the brain. And then rho here, which is a particularly interesting state, which is often called the heartbeat state, is completely constrained to the horn. So what this tells us is actually these three kind of clusters are actually mapping three different types of behavior. So the top, the brain is actually it's clustering together stochastic behavior, kind of random movements of intensity. And the flag is actually associated with long transitions between high and low intensities, which might be associated with things like magnetic towers, where material is being built up due to magnetic pressure and then eventually being offloaded onto the black hole. And then this horn is associated with flaring, which is usually associated with rapid inflows and outflows of material in the accretion disk. So one thing we wanted to look at here is the split across different clusters. Does this mean that Bologna kind of overfit his modeling? We personally do not think so. So here, this means that actually these classes might be built up of kind of three main building blocks of these kind of flaring effects, the long transitions between high and low intensities, and the stochastic behavior. But within these different clusters, the actual Bologna's classes are still well constrained. And one way of kind of breaking this down is by looking at what we call closeness metrics. So this first one is the idea of taking the average position in this UMAP projection, and then trying to compare the distances between these average points to see if there's significant overlap in the distributions. So actually, for the most part, you can definitely see here, rho is very different to almost every other class. Its distribution is very odd, but there's significant closeness here of, for instance, the alpha class and the nu class, and beta and the nu class, which from this we would think perhaps there's some similar structure, similar behavior going on here. So let's take a look at another way of looking at closeness by looking at the closest neighbors of each point. So here on the bottom row, we have when we look at a particular point of a given class, and we look at its nearest neighbor in the UMAP, what percentage on the x-axis is of another particular class. So straight away you'll see there's this bright kind of diagonal here, which indicates that the closest neighbor of a given class is itself, which is a good result because it means that both the network is picking up actual meaningful features, and also Bologna's system does seem to be actually robust. But there's a few kind of major points here. So chi ends up being a closest neighbor of a lot of different classes, generally just due to the fact that it ends up overwhelming the data set. It's 3/4 of the data set. It's going to end up being a nearest neighbor usually. but there's a few interesting ones. Particularly interesting to point out is alpha and nu have significant overlap in this particular metric as well, which would imply there might be some actual structural similarities here, where these might actually be a real physical thing. Okay, so my summary is we created an autoencoder that extracted complex features from observations. We managed to relate together segments of light curves autonomously with almost no input from humans. And the network strongly agrees with human models of GRS 1915's behavior, but GRS 1915's behavior might be made up of three kind of main building blocks of stochastic movements, flaring and dips, and lengthening transitions. I'm happy to answer any questions.
Thank you very much, Ben. Any questions from Ben first? You first?
Me first?
Yeah.
Okay, thanks. Very nice. So when you do your autoencoder, you kind of reduce your light curves to
to a small
features.
kind of,
How big do you need that space of latent features to be in order to be able to reconstruct the light curves?
So we use 16. Basically, as I was training the network, I went as low as possible until we were getting really poor reconstructions. And 16 was a nice level of, it was as small as possible, but still managed to recreate fairly well.
So you can say 16 is the
Yeah.
amount
You might
of
be able to
features
push it a
you
bit
need.
further. But
And are the light curves all of the same length?
yes, 256 seconds.
Yeah, that makes it much. Thank you. Yes, go ahead.
Yes, thank you. So I'm a visitor here, gravitational wave instrumentalist. So many of these things are,
They overlap a lot, yeah.
well, you would say, but I'm also thinking like there's three axes that you're talking about and all the different classes. Can you say something intuitive about it for me to
Yeah.
understand what I'm looking at?
So the three axes
how to
are,
do something that
Yeah.
works, and it seems like you got good work, so that's good. But it, to me,
Yeah.
it's like just a graph. Think it would be nice for me to understand a bit.
yeah.
what I'm looking at.
So the three axes they are built by UMAP to make a manifold. So it assumes that all of the data in the higher dimensions is on a uniform manifold. It's a kind of a constant density. So I can't give you a physical intuitive sense of the numbers for these UMAP stuff. But the best way is if you were to look in high dimensional space, stuff which is close here is close in high dimensional space. It's just supposed to be trying to visualize. In interpretation wise, the different clusters contain different types of light curves, so which are associated with different phenomena. So
it's just shapes of light curves when you call alpha.
yeah. So for instance, if I take alpha, for instance, so let's take lambda, for instance. The behavior for the stochastic behavior might be contained within here, and then a transition might be in that weird flag shape, and then flaring, for instance, of the row class is contained within that form.
Okay, thanks. Sorry.
No problem.
Okay, I think we have to move on. Thank you. Thank you very much. Okay, saving the best until last. Zoe Laconte is from London, in the UK. Amongst her interests, she unfortunately had a professional netball career mixed, which she's playing for the University of Southampton, and broke your wrist. Oh,
Yeah.
yes. So yeah, unfortunately, and she also enjoys watercolors. She is going on to do a PhD at the University of Durham in the UK, working with Dimitri Gadotti. And she's going to do something quite different today, and she's supervised by Martin Alvis, doing a project called Lunar Farside Radio Arrays, a preliminary site survey.
Yeah, so afternoon. Yeah, so I'm going away from the high energy and onto radio arrays on the lunar far side, a site survey. So we have a gap in our astronomical knowledge during the Dark Ages, which was a period prior to star formation, and I'm looking specifically at redshifts 30 to 80. During this time, the universe dominant baryonic content was neutral hydrogen, and this has a hyperfine transition spin flip, which is shown in this diagram here, that emits a 21 centimeter signal. So this highly redshifted signal is the only observable signal of this era. And we wish to look at it with a 10 arc-minute spatial resolution. And there are two methods to observe the dark ages, which is the global 21 centimeter signal or spatial fluctuations. So why we want to look at this signal is because it could test the standard cosmological model. And there has only been one detection of it this far with the EDGES experiment, which finds a 78 megahertz signal at around redshift 17. So this was during cosmic dawn, which is later in the period which I wish to observe. However, the standard cosmological model, which is highlighted here in yellow, is far off from these results, and they appear to be 3 times deeper than the standard model, and this cannot be explained by adiabatic cooling. So the interferometer, which I wish to observe these signals with, would be looking between redshifts 30 to 80, corresponding to the 17 to 46 megahertz range with a spatial resolution of 10 arc minutes. This then requires a 200 kilometer baseline radio interferometer. So why haven't we observed these signals before? Well, it's because on Earth, below 30 megahertz, we produced radio frequency interference, which would contaminate the instruments. And so we require a location which is radio quiet, and we determine this to be 90 dB, which would be where the signal is, the radio frequency interference is 10 to the 6 times greater than the signal we would actually be observing on Earth. And so within this boundary, which spans 800 kilometers, I have located 8 craters which just appear in this image to be of size where I can do a preliminary site survey. Now, as you can see on the far side, due to tidal lock-in, it means it will always be consistently radio quiet. However, the orange in this image is elevation, which shows that the far side is an extremely mountainous place. So in order to do my site survey, I use the Lunar Orbiter Laser Altimeter, which is one of the 6 instruments on board LRO. Now, this emits 5 simultaneous pulses, and these laser pulses reflect off the lunar surface, and using half their time of flight and the spacecraft position, we can measure their pulse broadening in order to get the roughness and the topography of the surface. So each pulse illuminates 5 meters, and their detectors are aligned during the daytime of the spacecraft. So in the downtrack direction, we have a 57 meter spacing between the spots. And so this means that that would be the minimum scale which we can create our surface and roughness maps on. However, because of limitations on the data, I've actually done this on a 200 meter scale in order to consider about 4 spots. Yes. And so there is also a lolar anomaly that I encounter, and this is when on the night side the instrument gets too cold and the thermal blanket retracts the detectors, misaligning them, resulting in only 2 of the 5 spots being detected. And this is shown in these maps of Daedalus. So in the left-hand map, this is just of the whole scope of the site. The central map is a zoomed-in image which shows the track coverage and the elevation measurements. And then finally, this is the pulse broadening measurement, which gives us a roughness measure. And so here you can see that the anomaly really is observed. So these are the 8 sites which I have observed, and these are their interpolated elevation maps. By interpolating the maps to a 200-meter scale, we've reduced the effect of the anomaly, and we're able to smooth over the surface. So I have then created slope maps in order to observe how well a rover would be able to traverse across the surface. So here we just have it exaggerated by about a factor of 6 in the elevation axis of Mare Moscoviense, and this just shows us that the Mare floor is extremely flat, whereas we would not be able to traverse any regions which are outside of the blue colour. And on the left-hand side, I'm just showing a axial rover, which would be the kind of thing used to deploy such an array. So then I have also created roughness maps from the interpolated data rather than the pulse broadening data. And these are created by finding the root mean squared of a 3x3 kernel across the entire grid. So on the 500-meter scale, we see high levels of roughness. On the 200-meter scale, we're actually able to identify areas of smoother terrain that we would be able to deploy an array. And on the 100-meter scale, this is where our limitation is, because you can start to see the track errors. So I've also created a figure of merit in order to compare the 8 sites. And this comprises of the site size baseline ratio, the Gini coefficient, which is a measure of the clumping of roughness. So sites like Korolev and Mendeleev will have a very low Gini coefficient because of roughness is dispersed across the whole site. And these sum to make a total point of 25. So just highlighting Mare and Jenny, and this shows that there are these gates which open pathways in order for a rover to traverse through, allowing this site to have be further studied. And just highlighting that slope threshold is critical for the array baseline, because going from 22 degrees to 24, the number of sites with orthogonal baselines above the limiting 200-kilometer baseline increases from 1 to 4. And finally, the site ranking, I have determined that Mare Moscoviense, Mare Ingeni, and Apollo are the best sites for these given thresholds based on the engineering aspects of the rovers. And if we're able to achieve the scientific goals, however, with a smaller array, then Tilskovsky and Daedalus can still be considered. Whereas these final 3 would no longer be considered for further study. So these are the 3 best sites, going from Mare Moscoviense, Mare Ingeni, and Apollo. So in summary, we wish to observe the 21 centimeter signal because it could constrain cosmology from the dark ages. And the far side of the moon is an exotic location for a radio interferometer, as it acts as a shield from radio frequency interference. Mare Moscoviense is determined as the optimum site for the interferometer. However, the other 3 sites can still be considered. And here I've just shown that working with Iris Fernandez, we are aiming to have better elevation measurements for these sites at smaller scales, which she has created in red here, whereas the Lola data is in the black line above. And this is just from creating a mosaic from narrow angled camera images with the Lola data. And I would also just like to highlight that the sites surveyed here would need to be protected from future contaminating interference. Yeah, thank you.
Thank you very much, Zoe. Any questions for Zoe? Yes.
Yes, thank you very much. This morning I gave a talk here about gravitational wave detection, or building a gravitational wave detector on the moon as well. I was reminded of the sharpness of dust and all kinds of things there, because we don't have erosion and things like that. I saw your rovers rolling out a cable.
Mhm.
It might be cut by these kinds of things. Is that something you are thinking about? Or?
Yeah, so this would have to be thought about by the engineers, which would create these rovers, and it would also be that the rover I showed is one that would be on Mars, so they haven't actually thought about this for the moon yet. Yeah.
And when are you launching?
2025.
2025.
Yeah, no, I'm joking. No, yeah, there's
there's also a group in the Netherlands who are from Hubble University. I don't know if you're working together with them, but yeah,
Oh,
I'm
amazing.
trying to poke them that you should team up and make these cheap.
Yeah, amazing. Thank you.
Okay, any other questions for Zoe? Yes, Josh.
Is there any potential disaster with the moon becoming more and more populated with hardness and everything that follows? So many satellites around the moon that you have trouble staying quiet on that side.
Yes,
I
yes.
just saw something, I think, in Space News a week or so ago about somebody that was in a constellation. This is how everybody's downlink needs constellation around the world.
Yeah, so this is sort of the reason why I've focused on this, because this just highlights that for a telescope of this scale, there's really only 3 sites that we can consider on the whole of the far side of the moon. So this really shows the urgency to protect these sites. Yeah.
Okay, any more questions? Right, thank you very much. They come to our top.
Yeah, sure.
I don't know if